Hello everyone. In this video, we are going to talk about the rotary encoders, the components that are very necessary in conjunction with motors or anything that is spinning if you want to measure their angular location, angular displacement or anything, right? You have to use a rotary encoder. So in general, there are two types of encoders, absolute ones and incremental ones. Incremental ones are the ones that you see the most. They are most common. They are much, much cheaper than the absolute ones. And for instance, like this one here, which is a HW040 and other versions of that, they're very cheap, like something like $1 or so, and they give you the relative position compared to the previous one, right? So they are just incremental. They give you steps, what we call, in each direction, and the absolute ones that give you basically the angular position. So these ones give you angular positions like theta, but these ones are basically giving you delta theta. These are relative. So we're going to see the difference between them, and I'm going to show you also here one of these basically rotary encoders here that is incremental. I have connected it to Arduino. I show you how to connect it and how to read the values with the code that I have, and we're going to go from there. So first thing is, let's look at the incremental ones that are the most common. So what you mostly have is a COM point, an A and B, but in general, you'll see that they have 5 pins most of the time. So you see they have a clock, they have a data, they have a push button, they have basically a ground and a 5 volt, or we can change it to another voltage too, but they are mostly working with 5 volts. Now, most of them, not only you can spin them in either direction, you can also press them down, and that is basically this push button. Okay, and you can use that to do something special, like for instance, you can reset your readings whenever you push it down. So they have basically two functionalities. So if you look inside of them, you'll see that there are a bunch of contacts here and contact zones. So these yellow ones are like contact zones. And you have these two contacts, A and B. And depending on which direction you are rotating, okay, either first this pin at A will come into contact with these contact plates or contact surfaces, right? So here, if you go in this direction, first B comes into contact, then A. If you go in the clockwise direction, basically first A comes into contact, then B does. So one of these contacts will happen a little bit earlier than the other one. And so if those contacts corresponds to some signals, then one of your signals is going to be a little bit ahead of the other one. And based on which one is ahead of the which, if A is ahead of B or B is ahead of A, you can determine the direction of the rotation. So that is the essence of how these work. So how many of these contact zones are inside of it? That depends on the resolution of your encoder. For instance, the one that I want to show you today, this HW40, that has basically 30 of these counts, or 30 pulses, or 30 we call detents. We talk about that per revolution. So every basically 12 degrees, right, which is equal to 361 full revolution divided by 30, every 12 degrees, it gives you one pulse. So basically your resolution is about 12 degrees, what you can get out of here, okay? And of course, you see that it works with 5 volts, but can you get it with 3.3? We'll talk about that as well here. So first thing is, what is detent? Detent, you can see here, it says that it has 30 detents, right? So we want to learn about this term. Detent means what? Detents are the points, the clicks that you will fill when you are turning a rotary encoder. As you turn a cheap common rotary encoder, you'll see that it basically makes contacts, right? And then release these contacts and so on. So basically what you have is a bunch of touches, a bunch of small mechanical notches and springs inside the encoder, which every time you have a contact with one of those contact zones, right, you're going to see one kind of small click. You feel it under your fingers. That is a detent. Now, most of the time, these detents are basically happening, these contacts, these physical contacts in the notches with the spring forces, they are happening at the same time of the contact. Sometimes they are not in phase with contact, they are a little bit shifted. Okay, so it's not like all the time the detents are exactly right on the top of those mechanical contacts, but most of the time they are. Okay, so here that is this part that they do not necessarily always align with the increments in these encoders. Now, as I said, one of these contacts between pin A and these contact zones or B happens a little bit earlier than the other one, and that is basically creating two pulses, one A and one B, where one is ahead of the other one. This type of encoder is what we call a quadrature encoder. Okay, so what is a quadrature encoder? So here, one of the signals is about 90 degrees or a quarter of a cycle ahead of the other one. That's where the word quadrature comes from, because one signal is a quarter of a period of a signal ahead of the other one. And you can see that here, right? So if this is the entire period of one pulse, right, going up and down, you see that this distance that one is ahead of the other one, if this is t, that distance here is about t over 4. Okay, a quarter of the signal. That's why we call it, or 90 degrees phase shift. That's why we call it the quadrature, basically, encoder. And as I said, depending on whether A is ahead of B or B is ahead of A, you'll see that it indicates a different direction. So you see here, for instance, if you look in this bottom one, you see that A is starting here, right? If you look at the rising edge is here, but B already has started a quarter of a period ahead. So say B is leading A. And that is an indication in this case that it is going counterclockwise. But if on the other hand, A has started ahead of B and we say A is leading B, you can see in this case, right? Look, this rising edge is ahead of the one in B, then that means a clockwise rotation. Okay, so by looking at these pulses, you can basically find the direction of rotation. Now, what about the change in the angle? Well, all you need is to count the pulses, because per pulse you have one contact. So when you get one of these pulses, that means, for instance, if the direction counterclockwise is positive direction, once you see one of these pulses, what does it mean? It means plus 12 degrees for the ones I'm talking about. Or if it's going clockwise, that means negative 12 degrees, correct? So this is basically your resolution. And by just counting the pulses, you can easily determine the displacement, really. So it's not really movement, it's a displacement, I would call, not position. And you can get the direction as well. Good. So a few things that we need to talk about this specific encoder. One, and many of these material that I'm showing you here are coming from these three websites. And the first one is the book, but mostly these two websites, okay? This circuit designer with that spelling, and this build electronic circuit. So some of my material and the code are coming from these. So first thing is, for this specific encoder that we are working right now, Does it support 3.3 volts as opposed to 5 volts? Can you run it with 3.3 volts? The answer is yes, it does, but of course the output signal is going to be weaker. Okay? So yes, you can connect it to 3.3. The other one, can I increase or change the resolution of this encoder? Well, remember it was plus minus 12 degrees, right? So can you go to 6 degrees or so? Well, not naturally, because these contact zones that you have, in this case, there are only 30 of them in this encoder, okay? So if you want, you can get another one that has 60 or, I don't know, 120 or something, but not this one. So if you want to change this, the only ways to do it is you can use a different gear ratio on your system, okay, or have some software algorithm to interpolate between the steps based on the time. But naturally, no, you cannot do it. Another thing we have is, as you'll see in the code, when I run this code, I have to use interrupts. Now, what is an interrupt? We'll talk about it in a separate video here. Not in this video, I mean in one of the future videos, but here we have to use interrupts. So why do I need to use interrupts, and can I run this without interrupts? I'm gonna answer that question, and again in a separate video later I'll tell you what interrupts are. That needs a separate video of its own. So first of all, can I run this without interrupts? Yes, but it's recommended to use interrupts, especially if you're going to rotate it at high speeds. If you don't, then you might miss some pulses and you don't get accurate results. So if you want to get accurate and nice results, it is important to use interrupts, especially if you have to spin the shaft fast. Now the question is, why do I need interrupt at all, right? Why is it that I need the interrupts? The reason is, most of these encoders, especially the quadrature encoders, their signals are changing very fast, okay? Their periods are very short, their frequencies are very high, their signal is changing fast, and your microcontroller might not be fast enough to read the changes in the signals, count all the pulses and everything, okay? Therefore, you can have some pulses missed and not get the accurate reading. Okay, so the changes in these encoders can happen a lot faster than your microcontroller can catch up. So what would you do with interrupts? Why is it that you might say, well, my microcontroller is fast enough? Well, most of the time it is, but remember, your microcontroller, the only thing it does at the moment is not just to read these pulses. It has other things to do. Okay, it has to look at all of the inputs, outputs, the program and everything. It has lots of tasks that it is doing. One of that is reading the signals from an encoder. And here with interrupts, you're basically prioritizing and saying, hey, I want you to, when the signal of the encoder is changing, when anything in this encoder is changing, I want you to put everything on hold for a moment and just look at readings of this encoder and try to read everything that you can as fast as you can and put everything else on a backlog for a second. So do an interruption in the rest of your operations while you're reading the encoder, okay? This way, you make sure that you're not missing anything while you're performing other tasks. You're changing the priorities and which one should be basically taken care of and be the main focus of your microcontroller. So this way, even if your microcontroller is doing other tasks, as soon as the encoder signal changes, it puts them on the hold, come here, reads the data, don't allocate any of its resources to anything else so it can read the data without problem, and this should get much better readings, okay? So that's one of the things in the software. You have to have some interrupts, and that is what you can see here in this code that I downloaded from one of my resources. You see that there is interrupt used. The other thing is debouncing. So remember I said there is mechanical touches, right? So these pins at A and B are going to come and touch these contact zones. So there is mechanical touch. And anytime there is mechanical touch, there is always the chance of what we call bouncing. So what is bouncing? So these mechanical parts, when they come into contact, they close the circuit, you're going to get a pulse. And then, because every part has some stiffness to it, then they might deform momentarily, lose the contact, the circuit goes open, and you basically get some basically fictitious or false transitions or false pulses because your pin bounces off the mechanical contact. So to avoid reading extra pulses because of this mechanical bouncing, one of the things you have to do is to do a debouncing, which is eliminating those spurious signals and pulses which are happening due to mechanical vibrations and contact, no contact situation in your rotary encoder. So how would you do the debouncing? There are different ways to fix the debouncing. One of them that is very common is to do it in the software. So you do a software debouncing by using delays and state checking. Okay, that's one of the common ones. And here is how you do it in Arduino. So the way you do it is you put some delay in your interrupt, okay? And make sure that basically after some delay, the system state has really changed. So let me show you what it means here. So look, the encoder position, you started initially at 0, the last time it at 0, and then you wait each time for 5 milliseconds. Then what? Look, it says read the current time using the function millis. Okay, remember the last time is 0 before you start. Read the current time if the current time minus the last time is bigger than 5 milliseconds. Then what? Then go ahead and do digital read 3 if that is equal to high. Change the encoder position, make it bigger because you're rotating, let's say clockwise, if clockwise means positive in this case. And if not, you're going counterclockwise, go ahead and change the encoder position negative. And then update your last time to the current time that you read. So you see, I'm only changing the encoder position if and only if at least 5 milliseconds have passed since my last reading. Okay, and hopefully this 5 milliseconds is enough to get rid of all those vibrations and your pin is sitting properly on that contact zone without getting off of it again, and the debouncing can happen. So here you are using some delay, and that is how you are basically going about debouncing. The other way that you can do debouncing is by applying a low pass filter using RC circuits. You know that RC circuits, if C is the output capacitor, can be used as a low pass filter. So that is what you have here. You see that is my encoder, that is my Arduino, and you see that I'm using capacitors and resistors, and these pins are taking the voltage across capacitors, as you can see here and here, right? So basically, they are reading the voltage off of capacitor, which is a filtered version of the input signal. And for that reason, you can have what? You can have a filtered version, a low-pass filter version on all of those transitions, all of those bouncings that can be considered like a high-frequency signal. You can filter them out. Okay, and then finally, another way that you can do it is called state-based debouncing, which is basically to check the encoder state over a bunch of samples rather than reacting to every transition. So here you're going to look at a bunch of samples, okay, and make sure that it goes stable before you do the reading. So let me show you that one here. So for instance, you say that here the last state was low, the current state is what you want to read, the encoder position is 0, right? Then you have some debounce time of 50, last debounce time 0. So look what you do. First, you're going to read the pin number 2. Then you say if the current state is not the same as previous one, so your current state has changed compared to the last one, then what? Go ahead and read the time that has passed since the beginning of the program using millis and give it to this variable, assign it to this variable last debounce time. Now what? Now when you come to the if, read the time again. If the current time minus the last debounce time, the last time that you read it, is bigger than this 50 milliseconds, then what? Then again, depending on the current state is high or low, go ahead and consider a clockwise or a counterclockwise rotation and change the encoder position, and then say what? Then say the last state equals the current state. So update the current state, right? So here you see that's quite a bit similar to the last one, except not only you have the time that should have passed, okay, also your state should be different than the last state. But basically, all of them are similar. Hey, be a little bit patient. Don't read it immediately. There might be some jumping, some bouncing between mechanical elements. Wait a few milliseconds, make sure the state has changed, or physically put some RC circuit on it to filter it, then do it, okay? So you have accurate readings, and also make sure you put interrupts in the system so that if the microcontroller is busy doing other things, as soon as the encoder value changes, it puts everything on hold and read that. So you see, just communicating with an encoder has a bunch of technicalities. And it's not just about here contacting 5 of these pins to 5 of these basically outputs of your encoder, right? 5 of the Arduino pins to these 5 pins, and just read the data. You have to make sure that you observe some stuff if you want to get accurate readings. So this is what this was for an incremental encoder. Now, before I go to absolute encoders, let me show you. So this is my code. And when I say my code, it doesn't mean I wrote it really. So I should not call it my code. It's the code I have for demo. I got it from this second website, okay? This Docs Circuit Designer. So it's not really my code. I'm just showing that to you. So here you see that the clock is sent to pin 2. The data is sent to pin 3, and the push button is sent to pin 4, okay? And then, of course, you have 1 to the 5 volts and 1 to the ground of the Arduino. So the first thing is you have the encoder position. You started at 0, and the last encoder position you started at 0. Now, you see one thing here. Again, when we talk about the interrupts in the future, I'll explain that, but you see that the type of the encoder position variable is a volatile variable, not just a regular integer. And you might say, what is this? Well, here you remember that when you use an interrupt, okay, when you use an interrupt to change a variable, and I'll show you this interrupt here is doing this reading and changing the variable. When you do that by declaring a variable as a volatile, you are making the compiler to not do the optimizations that it typically does on other variables for reading and writing them, and basically skipping that optimization and making the reading and changing faster. Okay, so you are saying, hey, don't do optimization for read and write of this variable. Don't waste time. It is going to change any moment because the person might just turn that knob, okay? And it is being managed by an interrupt. Then you see that I also have last clock and current clock, okay? So you see here, if you go to the code in the setup, of course, I make my clock data and the push button as basically input, but with a pull-up. So here I have not used external resistors, external pull-up resistors on these 3 lines. Okay, but if you see here, look, you see that sometimes these guys are connected with resistors, but sometimes you are using the built-in resistors. Okay, so you say input pull up. So not only it receives the signal, it has a pull up on those pins, so you don't need external resistors. And then for changing the encoder position, you are using an interrupt. Again, this needs a separate video of its own, interrupt, but you're attaching an interrupt to what? To the digital pin for the clock. And you have the read encoder, which you're going to see down here. That is your interrupt service or function for reading the encoder. And then you say, when would the interrupt get into action? Whenever there is some change in this variable. Okay, so as soon as you see a change, as I said in encoder, go ahead and activate the interrupt. You start the serial communication for showing the values, and first you read the clock before going into the program. You read it one more time. Now in your loop, you see that I say if the encoder position is different than the last one, go ahead and get that encoder position multiplied by 12 and show it as the angle change. And then this new position, assign it back to the last one. So this is basically all you do in the loop. You get the encoder position. Where does encoder position come from? It does come from your interrupt function. This one, this read encoder. Once you get that in the interrupt, you multiply it by 12. Why 12? Because remember, you have only 30 positions, 30 of those clicks, and each click corresponds to 12 degrees. So here by multiplying by 12, I have an angle change in what? In degrees, okay? So that is what I'm gonna show on the serial, on the basically the serial monitor. Good, so that is what my code is doing, reading and showing the changes. Now, if a button is pressed, if the push button, if the pin SW is low, which means it is pressed, go ahead and reset the encoder position. So regardless of where it was, set it to 0 now. So anytime you press it, okay, it is going to reset the numbers of the encoder, and you're going to show that, hey, it was reset to 0. Good. And then you see that here I'm showing what I'm using a little bit delay to wait for the button to be pressed. So it says as long as you are pressing that button, go ahead and put some delay. So this simple while loop with a simple line of delay is just waiting for you to release it, right? So it doesn't have to show the rest of it. Good. Now this is your interrupt read encoder. You see it doesn't need any input, right? And what it does is it reads the clock and assign it to the current clock time. And if it's different than the last clock time, and if what you read from the data is different from the last clock, then it goes and what it is going to basically change your encoder position. Now these 3 dots that you just saw here, they were hiding this line of code, right? And I was thinking, where is that line of code? Because you have to either go up on the encoder position or go down, and they were just hiding inside these 3 dots. So I clicked on it, expanded it, and now you see that if they are not equal, then you go, then increase the encoder position, else you're gonna decrease the encoder position, and of course you're gonna update your clock time. So you see that here, basically we are using interrupt and checking on the state. We are not using a delay for reading, so the debouncing is not here used necessarily because I'm really being very slow by rotating it. But if you want to go fast and there is better chance of debouncing and everything, it is really a good idea to put one of those 2 different methods that I showed you inside your code to do the debouncing, especially this one, which has a simple delay-based mechanism. So here I'm going to send it directly to the Arduino, and I'm going to show you the serial monitor. And you can see that as soon as I turn my encoder, you are going to see the results. So you see right now, there is nothing, but let me take my hand and turn this one for you. So you see, I'm going in counterclockwise. It goes -12, -24, 36. Now if I go back in the clockwise direction, it goes positive, right? So you see that the angle is changing by 12 degrees each time, and there is no limit. It's not like a single turn. It can go as many turns as you want, and as soon as you press it down, look here, it goes and resets to 0. Okay, so this is how you work with this simple $1 rotary encoder. Now, what about absolute encoders? Well, absolute encoders are a little bit different because they give you the exact angle. They don't give you displacement. They give you angle. So they have to have a way to read the angle, not the change in the angle. Okay, and that needs a little bit more sophisticated system, and that means they are more expensive. And you can see them anywhere from 40, 30, 40, 50 bucks to some very advanced ones like this SICK absolute encoder that is about $800. Okay, so these absolute encoders are typically very expensive depending on the resolution, their speeds, and everything, but they are more sophisticated and they are more expensive. Okay, so they look like this, or there are other shapes of it that you can see, but this is a typical absolute encoder. So how does absolute encoder work? Now, I don't have a physical absolute encoder here with me to show you. Maybe in one of my future videos, I'll add that in conjunction with another component to show you. But right now, I don't have it, so I just explained the theory behind it. So what you need to do is, first of all, you have a disk, which we call the code disk or the code wheel. And that is a fundamental component that is attached to the shaft that is spinning, and it has some specific markings on it, like lines, segments, regions, and so on. And there are either binary or gray code values on it, which will allow the system to read angle. Now, what does that mean? So let me tell you. So there are two types of markings typically on it, either binary or gray code encoding. What is that? So here, if you look at this gray code, that can explain it very well. So this disk that you attach to the shaft and it spins with the shaft, if you look at it, basically, it does not have a single kind of transparent or hole in it. There are several sectors, and there are 4 layers in each radial direction of holes, okay? And there are 4 layers here that you can see they are opaque and they don't let the light pass. So some of them don't let the light pass, some of them are kind of transparent, or there are a hole in them, there is a slot in them, and they let the light pass. If you want to see a better picture, you can look at here at this optical encoder. Right, so you might have some LED light on one side. There is this disk. It has a bunch of slots on it, which are kind of small, basically openings in the disk. And on the other side, you have a photodiode or a phototransistor. And anytime that one of these holes comes in between the diode and the LED, or the transistor and LED, the light will pass, so it receives it. Again, most of the time it's a phototransistor, not a photodiode. So the circuit goes closed or open and you get a pulse. And then the next one comes, the next pulse comes. And by counting the number of pulses, you know how many of these slots, which are at equal angular displacement, you count them and you see how much it has rotated. Okay? But this, the way it is right now, this is just incremental. Why? Because all you can see is how many of these holes you have, they have gone between the diode and the phototransistor. you don't know which one of them. So if you just use it the way it is, it's basically incremental. But if you get it a little bit more sophisticated, you can read actual angle. How come? Well, look here. Here in this radial direction, as I said, instead of one of these slots, you have four of them. Okay, in this direction, you have three and one opaque, or one closed. In this direction, you only have two, then one closed, then one whole again, and so on. And if you look, because you have four of these, this is kind of like a 4-bit combination. And here, instead of one LED, you need an LED array. You need 4 LEDs that each one of them, and typically they are laser LEDs, each one of them can either pass their light through one of these slots, or it gets basically restricted and doesn't go through, right? Because this black part does not let the light pass through. And on the other side, you have an array of phototransistors or photosensors. So these 4 ones here, they either get the signal or not. For instance, in this case, the top one, which is this area here, it does get a pulse. These 2 in the middle, they don't get anything. And that last one here also gets something. So if you read that, that counts like a 1, 0, 0, 1. And you know, in binary system, this is corresponding to what? This is 1, this is 2, this is 4, this is 8. So that number is actually 9. So when it receives this combination, means the slot number 9 was in front of the arrays of LED. So you see now each one of them has a specific identity different than the other ones, not like this case that they were all the same, right? They were all either 1 or 0. Now you have a combination. So you end up with a disk like this, where each one of them, you can see it corresponds to a number. So these 4 are, let's say if they're all white, it could be 0 or could be 15, and then you go to 1, right? So you see here that is 0, this is 1, this is 3, right? And then this is, if you look here, this is 2. Then here you have 2 and 4, you have 6, you have 7, right? So if you look at this order, and this one is like 15, if you follow this order, you see that these numbers are not in the logical order, right? So 0, 1, 3, 2, 6, this one is, for instance, a 5, right? Let me just write them. This is 8, this is, this is a 4, this is 4 plus 8, that is a 12. This is a 13. This should be a 14. And then this one is just 8. This one is 9. And finally 11 and 10. So you see that the order that you have here is not exactly going from 0 to 15 one by one. So what's good about it, in this sequence, which we call it gray code encoding, what is this? Here, this is a special type of binary where only 1 bit changes at a time, reducing the chance of error. What does that mean? Well, if you go from 0 to 1, you see the only thing different between these two is only 1 bit. That is this guy that went black from white. So between each 2 neighbors, there is only 1 bit of difference. If you go from 1 to 3, look, both of them had the first one white, the last one black, right? And this second one white. So the only difference between them this time is this guy. Then when you go from 3 to 2, the only thing different is this one. Then you go from 2 to 6, the only difference is this one. You go from 6 to 7, the only difference is what? This one. So each one of these combination with the one next to it has only 1 bit of difference, not several. So the chance of making a mistake is much smaller. But if you look at a regular binary coding, you see that if you look at these numbers, this is 0, this is 15, right? This is 14. This one is basically 13 and 12 and so on, correct? So you see that in this case, depending on how you call it, so if you call this guy like to be 8 and this one to be 4 and this one 2 and 1, you see that it goes based on the logical order, and this is 1 and this is 2 and 3 and so on. So this one is exactly the order that we count. But the problem is, if you look at each one with respect to the neighbor, there is sometimes more than one bit that is changing. Really? Yes. Let me show you. For instance, if you look here, these two, look at these two here. So what's the difference between them? Not only this last bit is different, also this second to the last is different, right? Or look at these. There are 4 bits of difference. So when you put it in that logical order, when you go from one to the other, since several bits can change, you have a bigger room for mistake. But in gray encoding, it's only 1 bit that can go wrong, so you have a smaller chance for mistake. So this is the difference between binary encoding and gray code encoding on a disk, or a code disk, what you might call. So that's the first thing you have. And of course, your sensing mechanism could be optical, like I explained for you with this wheel and with the arrays of LEDs. Or sometimes it's not the light that passes through this stuff. Sometimes it is a magnetic encoder. By the way, this is an appearance of an optical encoder, which is very, very common, and it is used a lot in lots of places. But in magnetic encoders, to sense the location, instead of light going through these slots, you have Hall effect sensors. And I'm going to have a separate video on Hall effect sensors. But these Hall effect or other types of magnetic sensors are going to sense the presence of the location of the shafts and these poles on the shaft that is spinning. And depending on where these poles are with respect to these Hall effects, they're going to generate pulses to tell you about the absolute position. So, of course, you have to have a mechanism for changing, right, the numbers and sensing it. And, of course, you need to do some final signal processing in order to interpret these signals that you get and find the absolute angle of the shaft. For instance, if you have a 12-bit absolute encoders, you can get any number from 0 to 4095. Now, the types of the absolute encoders, there is one category called single turn, there is another category called multi-turn. In single turn, they are really meant for one full revolution of the shaft. So you can only rotate the shaft one full revolution, no more, okay? And you get a single value that exactly tell you the angle from 0 to 360 with whatever resolution they have. In multi-turns, now you can, just like this incremental one, you can turn the shaft several turns, not just one, and they give you 2 numbers. One is how many turns you have turned. So it says like you have turned 10 full rotations, which is 10 times 360, plus what? Plus another number, which is where you are within a revolution, correct? So, for instance, they say 10 turns plus, for instance, 30 degrees, and this is all counterclockwise. Okay, so they give you these numbers, and you can find your exact position. Most of the time, these multi-turns one, they have higher resolutions as well. And when the shaft rotates several times, we are going to use them, but of course they are more expensive. So the last thing we want to look at is a comparison between absolute and incremental encoders. So as I said, the absolute ones, they give you basically angle. The incremental one give you an angular displacement. Now, the good thing about these absolute ones is you might say, why? Why would you need to get the angle as opposed to displacement? Why would you do that, right? What is the advantage? Because they are way more expensive. Well, one thing is they maintain their position. Because as long as this specific pattern is in front of me, I know my angle, right? But in incremental one, whether this one is in front of the light or this one is, I have no idea. So the good thing is, if you need to know cases that you need to know the absolute angle, even if you lose the power, right? And you don't need to do any homing, then of course the absolute ones are the way to go. So if you see a chance of losing power and you don't want to do homing requirements, you don't want to do it, then you go with absolute ones. The incremental ones, you have to do some homing to start from a known angle. And of course, if you lose your power, you're going to lose everything. You have to start again. Both of them typically send digital outputs. The resolution of them, most of the time, the absolute ones can provide higher resolutions. Okay, that's why they are more expensive, as I said. And of course, they are more complex. Now, about the direction for absolute, there is no need for direction. Why? Because when it gives you an absolute angle, you know whether you are on the counterclockwise side or on the clockwise side. But for the incremental ones, of course, you have to know the direction. Then, what about the multi-turn capabilities? So, typically, the absolute ones can have, most of them do have multi-rotation capabilities, of course, at the higher price. The incremental ones typically track one rotation, but of course, if your algorithm, like the one I showed you, keeps track of that angle, right? You see that I can go to bigger than 30 in this case. You see that here I passed, look, let's see. You see, I passed already above 360 degrees. So you can keep track of that as well. And about the speed, typically the absolute ones can handle higher speeds and they are less susceptible to noise. The incremental ones, they can handle higher speeds too, but they are more prone to noise. And finally, applications. Absolute ones are used in scenarios like some robots, CNC machines, and automations. Incremental ones used when you don't need the absolute angle, you just need to know relative ones like a position control, okay? So it all depends on, as I said, mostly, do you need to do homing? Do you need to know your position? If the power is lost, do you need to know your absolute angle or not? Okay, hopefully this video was useful to you. I could explain a little bit about the rotary encoders. I show you a code that is working and how you are connecting your encoder incremental to Arduino. And I'm gonna let you download this code from under video description, or you can go to that second website, as I said, and download the code directly from there. Thank you so much for your attention. I'll see you in the next video.